This is week 2 of the systems lecture, where we try to leverage the most out of the hardware we have to make models train faster. And last week, we talked about parallelism within a single GPU. And this week, we're talking about parallelism across multiple GPUs. So this is a picture you should have in your head. So we have a bunch of nodes. These are basically computers that each have a number of GPUs, usually 8. And within each GPU, there's a bunch of streaming multiprocessors, or SMs, which actually do the work. And you see that in green here are essentially the memory and the communication. So within each SM, you have a very small L1 cache. On a GPU, you have high bandwidth memory, HBM, which is bigger. And then you have these links that connect the different GPUs. So the way to think about it is that compute has to happen within the SM on these ALUs, right? And a compute needs inputs and needs to write outputs. And generally, the inputs and outputs can be relatively far. If you're lucky, they're on the L1 cache. If you're, say, less unlucky, they're in HBM. And now this week, we're talking about multi-GPU and multi-node training, where the data that you might need might be across on another GPU. Right, so the name of the game is how do you structure all your computation to avoid data transfer bottlenecks? Because we want to, remember, keep the arithmetic intensity high. We want to saturate our GPUs, make them go hum along. And generally, data transfer is going to be a lot slower, so that's going to be the bottleneck. So last week, we saw a bunch of different techniques to try to do that within a GPU, including fusion and tiling. So the idea basically is that instead of reading and writing from HBM, you can load into L1 cache or I guess shared memory, which is using the same type of has the same speed, and just work there on your local scratchpad and then write out to HBM only judiciously. And this week, we started looking at communication across GPUs and nodes, where we have to replicate and shard our models and parameters and optimizer states. And there, it's the way we do that will determine the cost. So here's a kind of I'm taking a little bit of liberty to put everything in kind of one hierarchy you can think, from small fast to big slow. So the smallest and fastest is on a single node, single GPU, you have L1 cache. That's extremely fast, but very small. And then you have HBM on a single GPU. And then between GPUs on the same node, we have NVLink. And then finally, we have NV switch. And of course, this is all in the NVIDIA ecosystem. So the idea is that many of the core concepts of minimizing data transfer are really the same, but now the mechanics are a bit different because L1 behaves differently than these kind of NV switches. So this lecture is going to be mostly about concretizing the concepts from the lecture in code. There's going to be a few new things, but Tatsu did an excellent job of giving you an overview of all the different types of parallelism. I'm going to try to anchor it in the code so we can more deeply understand what's going on. And then we're going to have, I'm going to refer to the standard out file here, which is the output of running this lecture. There were some minor issues I'll spare you of, where if you have multi-processing, then this framework doesn't quite work. Okay, so this lecture has 2 parts. In part 1, we're going to look at the building blocks, collective operations, which we discussed last time, how this is implemented in Nickel and PyTorch, and then we're going to do some benchmarking. And then in part 2, we're going to look at actually distributed training, data, tensor, and pipeline parallelism. Okay, so let's start with collective operations. So collective operations are these primitives that are used generally for distributed programming. And collective means that you have many nodes. These are actually quite old, from at least the 80s in the parallel programming literature. And generally, they provide a better abstraction than trying to manage the point-to-point communication yourself. So these are really tried and true primitives that have stood the test of time. So a bit of terminology. So world size refers essentially to the number of devices, for example, 4, and the rank, sort of confusingly, if you're used to kind of linear algebra, is actually just refers to device. So we have rank 0, rank 1, rank 2, and rank 3 if you have 4 devices. Okay, so the collective operations are as follows. Starting from broadcast, the idea is you have T0 on one of the ranks, and you just want to put it on all the other ranks, or all ranks. Okay, so that's very straightforward. Scatter is similar, but you have 4 values, and you want to put each of the values on different ranks. So each of the ranks get different values, not the same value. Gather is the sort of the inverse of scatter, where you have each rank having a different value, and then you bring them all together onto one rank. Reduce is the same as gather, except for instead of concatenating, you add them. All gather is the same as gather, except for you just do it for all the destinations. Gather was just rank 0, or rank 1 or rank 2, or any individual rank. All gather is you do it for all of them. And then finally, reduce scatter. I couldn't find a good picture of this, so I'm reusing the one from last time. Is like reduce, where you take a bunch of different values and you add them or perform other commutative operation on them and put it on one rank. But like scatter, you're going to be putting different pieces of the vector or tensor on different ranks. Okay, and remember that all reduce is equivalent to reduce plus all gather. So the way to remember this terminology is as follows, because it can get kind of confusing, like which one's all gather, which one's reduce scatter, is that reduce just means you're performing some associative and commutative operation, like sum or min or max or average. Broadcast scatter is the inverse of gather. And all just means all destination is all devices. Okay, so hopefully this is a review from last time. So actually, any questions before I move on? Since we're going to build on these primitives, so it's useful if everyone understands. Okay, so now let's see how this is actually implemented in, starting with the hardware. Okay, so here's classically what hardware for GPUs looks like. So this is kind of in the home. You have a computer, I guess, and you have your CPUs, and generally you have your GPUs on one node that communicate via a PCIe bus. And if you have to go communicate between different nodes, then this is all connected to Ethernet. So this is kind of typically how machines were built. If you buy a GPU and you're for gaming or something, this is kind of probably what your setup looks like. As we'll see, this is kind of suboptimal because there's a lot of overhead. When the data needs to get shipped from GPU to GPU, it has to go through the kernel, get copied into buffers, and then go through this kind of transport over Ethernet, and that introduces a lot of overhead. So what has happened in modern times with scientific computing and deep learning is that if you know that you're going to just string a bunch of GPUs together and do something together, then we're just going to hook the GPUs up directly, basically. So in the NVIDIA ecosystem, we have NVLink that directly connects the GPUs, therefore bypassing the CPU. You don't need to go through kind of the kernel of the host machine. And even across nodes, we can connect the GPUs directly via NV switch. So therefore, we're bypassing Ethernet. And because Ethernet was developed a long time ago, clearly not for these type of applications. So NV switch and NV link kind of skip all of that and just optimize directly for the type of workloads that we're interested in. So if you look at H100s, each each GPU has 18 NV links, generation 4 coming out. So that gives you a total bandwidth of 900 gigabytes. If you compare to these, it's certainly a lot faster than PCIe, and it's certainly way faster than Ethernet. In comparison, if you think about the cost of just going from the SM to reading from high bandwidth memory, that's still quite a bit faster by a factor of 4 or so. And of course, these numbers are constantly changing with the new Blackwells. This number is like 2 or 3 times more, I believe. Okay, yeah.
For the PCI, does it go through the CPU and then to another GPU, or it's direct between the GPUs?
So the question is for the PCIe, how does the data get transferred? I think it has to still go through the CPU. Was there another question? And the PCIe, it's developed for, things like, other things are connected to it as well, like your sound card or your SSD hard drive. So it's not really, it's sort of like a general purpose, bus for communication of devices, yeah.
NVLink also has a connection with CPUs.
Yeah, so the question is NVLink also connects to the CPU. We're going to see a bit later how, I think maybe just in this slide, how things are connected, yeah. So you still need to talk to your CPU, of course, yeah. Okay, so there's this command that you can run, and this produces some output, which allows you to see how the GPUs are actually connected. So I ran this on our cluster. There's 8 GPUs. I guess you won't be able to get 8 GPUs, but I guess if you could, this is what it would look like. And you see that between every pair of GPUs, there's MV18 connecting. There's also these kind of network cards and other things. Okay. So then network cards are basically what gives you the PCIe connection and the CPUs. So, so that's the hardware. So how do you use the hardware? So NVIDIA has spent a lot of time developing really good software on top of their, I guess, really good hardware. And there's a collective communication library by NVIDIA called Nickel. And this essentially translates the collective operations, which we looked at before, like all reduce, into low-level packets that need to be sent between GPUs. So this library actually does a lot of work because it allows the programmer just to operate at the level of, I need this tensor to appear on all the machines. And it just happens. Okay? So just a little bit of what happens is when you configure, set up Nickel, you bring up a bunch of devices, and there's some communication that happens to figure out the topology of the hardware. It optimizes the path between the GPUs, and then when you actually call these collective communication operations and then launch CUDA kernels to send and receive data. Okay, so that's Nickel. It's provided as a library, but Nickel is still a bit too low level to us because most of what we're doing is in Python. So there's PyTorch has this torch.distributed library, which essentially provides a clean interface for these collective operations. Now, from the comfort of your PyTorch program, you can just write all gather into Tensor on a Tensor, and it will appear on all the different ranks. It also has this nice, useful feature that it supports multiple backends for different hardware. So in particular, nickel, remember, was for GPU, but you can also run collective operations. Remember, this is not GPU specific. It's just for any set of devices. So you can also do it for CPU using this backend called Glue. So if you're debugging stuff on your laptop for your assignment, for example, you can use Glue and still be able to run things without even a GPU. So anyway, that's another advantage of having these high-level primitives is that they're much more portable than having to, only having something that's very GPU specific. Of course, the performance is going to really depend on the hardware, but at least logically, you can make sure your code runs. Distributed also supports other high-level things like FSDP, which Tatsu talked about last lecture, but we're not going to use this in this class because in the spirit of developing things from scratch, that's just what we're going to do. Okay, so let's look at some examples of how torch.distributed collective operations work. Okay, so there's this utility function I wrote, which you can take a look at it in the code if you want, which takes a function and just runs this. Basically, it's a wrapper around Python multiprocessing where it just runs 4 processes that execute this function. So when you're in this function, you should think about it as there's actually world-size number of processes running this identical function where the rank indexes from 0, 1, all the way to world size -1. Okay, so right now I'm stepping through just one of the ranks because lectures are not parallel. And so generally what you do is the first thing, the process needs to initialize itself. And you essentially, they need to kind of find each other, right? Because you're multi-processor, running a lot of processes, they need to connect to a single host so that they can know that each other exist. So note that this is not where all of the data goes. The data goes through nickel, but this is just for kind of coordination. And since we have a GPU, we can use nickel, otherwise you would use glue. Okay, so after you set up, so now we're going to do some stuff. There's this useful function called barrier, which basically waits for all the processes in your process group to get to this point. Right? Remember, everything is running asynchronously. And in some cases, you just want to have a synchronization point, so barrier does that. The reason I put it here is actually sort of for trivial reasons, because I want all these print statements to kind of be grouped together. But there's other reasons why you might want to use barrier, as we'll get to later. So I'm going to, for each of these groups, construct a tensor. So the tensor is 0, 1, 2, 3 plus the rank. So I'm going to print out for each rank before the all reduce. What does it look like? Okay, so here's what it looks like. Can people read that in the back? Yes? Okay, good. All right, so on rank 0, it's 0, 1, 2, 3. Rank 1, 1, 2, 3, 4, and so on. And notice that because it's async, the order is it's just out of order in whatever order it happens to print. Okay, so each rank has a different tensor, and then you all reduce. So all reduce, you pass in that tensor, you say, I want to sum it. In this case, I'm not going to do async, but you can do async which is useful for overlapping communication and computation. And then afterwards, what happens after all reduce? As advertised, basically for the first component, you add them up, you get 6. This you get 10, 14, and 18. Okay? So after all reduce, basically this tensor gets overwritten with the corresponding sum. So it's very, very kind of nice and simple to use. Okay, so let's do reduce scatter. So reduce scatter, I'm I'm going to create an input, which is has dimension world size, in which case this is 4. And I'm going to allocate an output, because reduce scatter is not going to operate in place. This is just going to be a scalar. So before the reduce scatter, this is what it looks like. I have my input as before. Output happens to be zeros, but it could be any value since I didn't initialize it. And then after the reduce scatter, where I pass in the input and the output, and I'm going to sum, then I get essentially what happens is that for the first component, I sum, and that goes on rank 0. For the second component, I sum, and it goes on rank 1, and so on. Okay, so as you notice, it is producing the same operation as all reduce, except for the output is sort of scattered across all the different ranks. Okay, so now let's do all gather. So I'm going to just directly use the output of reduce scatter, which is this, as the input. And then I'm going to allocate an empty array for the output. And then so before the all gather, the input is this, and the output, I guess, are just arbitrary values. And after I do the all gather, what happens is I get all these tensors to show up on all the devices. Okay, so this is just a kind of also an example. Hopefully now you're very convinced that reduce scatter plus all gather is just all reduce, because I computed exactly the same quantity as I did for all reduce. Okay, questions? Is this clear? Yeah.
In reduce scatter, are we keeping track of which index goes to which GPU?
So the question is, in reduce scatter, do you keep track of which index goes to which GPU? So by convention, the dimensionality has to be basically the world size. I mean, it could be a general tensor, but one of the dimensions is the world size, and it just infers that basically what you want to do is the output is let's say the input has to be basically world size, and then it knows that basically the corresponding computations go to each of the outputs. Yeah, you have to be a bit careful with making sure the dimensionality aligns. So going through this small examples can be helpful. Is there another question? Okay. So finally, we're now in this process that's running, and when you're done, you just clean up. Okay. So so far we've talked about these collective operations, a bit about how they're implemented in PyTorch and its Nickel and then PyTorch. Let's do a bit of benchmarking in the spirit of what we did in assignment or the first lecture, or rather the second lecture. We're going to focus on one node for now. So let's do all reduce. So I'm going to have this tensor of 100 million elements and a world size of 4. Okay, so I'm going to just allocate a tensor, and generally, as I think, as you hopefully can appreciate now, that when you benchmark, you have to really be careful to kind of clean your palette in some sense. Like in this case, I'm going to warm up, basically run the operation once, and then synchronize and do barrier. Some of this is, I think, probably a bit defensive, but just to be safe, so that all the kernels get loaded, and whatever needs to be kind of computed gets computed. And then I'm going to start the clock, all reduce, and then synchronize again and stop the clock. Okay? So now I can look at how long that took. Okay, so if I scroll down here, I guess this is not that informative. I should have printed in microseconds probably. It was, I guess, very quick. Some number of seconds. And now let's measure the bandwidth, which is the number of gigabytes that were actually transferred in aggregate per second. Okay, so the way we do that is we have to think about what actually gets transferred here. So there's a tensor with that element size, and the size of each element is, I think this is float 32, so that would be 4 bytes, and so that's the size in bytes. Okay, so now this is a little bit subtle. So how many bytes are actually sent or transferred, sent/received? So each tensor sitting on a rank has size bytes, okay, and it needs to send it to world size -1, other machines, or ranks rather. So but there's a factor of 2. So why is there a factor of 2? Because you're doing it all reduce, remember? So you need to send all the distinct elements into basically one place. It needs to get summed up, and then that needs to go back to everyone. Okay? So a rank needs to kind of send the input out and then receive the output. So that's why there's a factor of 2 there. And so the total duration is the world size times the actual duration that passed. So I guess we're just kind of assuming that if there's 4 processors, that's sort of like 4 times as much wall clock time that happened. And the bandwidth is just the bytes over the duration. Okay, so what do we get here? Is about 277 gigabytes per second. Okay, so I think for H100 above, I think I claimed that there was something like 900 gigabytes per second. Now, of course, as we know, your mileage varies depending on the size of the tensors and the exact number of devices and the weather and whatever. No, not the weather, but various factors. So your mileage might vary. So it's always good to benchmark to see what is actually the number of gigabytes per second you're getting. Okay. So reduce scatter is going to be very, very similar. So let's just go through this very quickly. So we created input, which is world size times number of elements. So each rank is going to have the matrix, and so we're going to warm up, and then start the clock, reduce scatter, stop the clock, and then see how long it took. Well, okay, that's not helpful. And then let's look at the bandwidth. So the number of sent bytes is no factor of 2 here, because in reduced scatter, remember all you're doing is you're sending your inputs into one place. If you just think about reduce, right? All the elements just go into one place, and that's it. And scatter just means that different components of your tensor are going to different places, but it's like a reduce. Okay, so if you do the same calculation, you'll see that I guess I get 70 in this case. So I don't exactly know why it's exactly 70 as opposed to some other number. I guess one could speculate that all reduce. Generally, there's more traffic that happens, and all reduces are potentially more optimized. I think that NVIDIA hardware has this kind of sharp acceleration that actually does sort of some of these computations in the actual network, which shaves off a factor of 2. But I don't know if that completely accounts for a difference here. There's a lot of stuff that happens in nickel that it's a little bit hard to kind of reason about the performance exactly, hence benchmarking. Yeah.
A question about the set bytes or the data bytes and how that was calculated.
Yeah.
Specifically, it looks like it calculates just like the data that's being sent right to the output. But what about like the inputs, the reduction step? I was wondering like how it gets the inputs to do the reduction.
So the question is, it seems like this is just the bytes for the output, and what about the input? So to be clear, I am assuming that the inputs just are already on the device, so I'm not counting that time, and just I'm just counting what needs to happen to do the reduce scatter.
Is this just a scatter operation? Or?
This is a reduce scatter operation.
So you need the reduction step also.
So this function does reduce scatter. So it's one operation.
I mean, like we counted twice in the previous because you were doing reduction, we counted for half the bytes and then for.
So you're saying that for all reduce, there's a 2x because you needed to reduce and then you needed to spread out again. For reduce scatter, I mean it's just a name. It's called reduce scatter, but it's really just a reduction. Okay, and you can also see based on this that if you do reduce scatter and you do all gather, each of those doesn't have the factor of 2. So when you add them up, you get a factor of 2, which is another way to see that all reduces twice. Okay, and there's some references you can go read about how to benchmark and these collective operations. Okay, so let's now talk about the distributed training piece. So our general approach here is going to be, I'm going to walk through a bare bones implementation of each strategy on deep MLPs, essentially. So recall that you generally are in the regime where the MLPs are the compute bottleneck and transformers, not the attention. So in some ways, even though this is a very simple architecture, it's fairly representative of the type of workloads that you'll see. Okay, so let's start with data parallelism. Actually, just one note is that data, tensor, and pipeline parallelism you can just think about them as different ways of cutting up either your model or your data, which hopefully I'll depict visually here. Okay, so in data parallelism, here's your model. Assuming it has 4 layers. Each layer of the MLP is just a matrix multiply, where this is the hidden dimension. And so the data is also a matrix, which is there's the batch dimension and then the hidden dimension. And data parallel just cuts along the batch dimension into essentially smaller pieces. Okay, so now each rank is going to get a different slice of the data. So let's do an example here. So I'm going to generate some sample data. So let's say I have a batch size of 128, hidden dimension of 1024, and then just generate some random data. Okay, so I have batch size by number of dimension, and I'm going to run this data parallel algorithm, or DDP. So here I'm going to, so I got past this data. There's a batch size and the dimension as claimed from before. Now I divide the batch size by the world size, so I get the local batch size. And that's how many, how big the batch size is on a given rank. And then I'm going to, based on the rank, just figure out which starting and ending indices of size, local batch size I need to access, and then get the corresponding data from that. So basically, I'm just reaching in and grabbing some subset of the rows based on the rank. Okay, so now I'm setting up the MLP here, and this is done very sort of bare bones, you could say. So here I am creating the MLP parameters. So each layer has essentially a matrix which is num dimension by num dimension. And remember, num dimension is 1024. And I'm going to create the optimizer. So remember, this function is running asynchronously on all the different, on each rank. So each of the 4 ranks is going to be running this with rank equals 0, 1, 2, 3. And now I'm going to start training. So for a number of steps, I'm going to do a forward pass through the layers, matrix multiply nonlinearity, matrix multiply nonlinearity. There's 4 layers here. Going to compute some loss. I don't really care what the loss is. It's just made up, something made up. And now I'm going to do the backward pass. So far, this just looks like I'm implementing SGD, right? And that's kind of the point. The only difference is now to implement DDP is that you just inject this line here, which synchronizes the gradients across workers. So what you do is for each of the layers, you call it all reduce, where you're averaging, and the thing you're averaging is param.grad. Okay, so it's just like you've kind of hijacked this someone's SGD code, and you're saying, wait, I'm actually going to just mix all the gradients after the backward pass. And then after you do that, you just update the parameters as usual. So from the SGD perspective, it seems like nothing is happening. I'm just running SGD, but someone has just mixed my gradients. Okay. So I guess just to print out some things. So data parallel, I'm printing out the loss. So one thing to note is that the losses are different between all the different ranks because they have different data. But after the all reduce, all the parameters are the same. Okay, so this is a kind of your textbook application of all reduce in ML setup. Yeah.
I was wondering, when each rank runs this all reduce, how do they ensure that they're all sort of at the same step, marching through the same step, or maybe that doesn't matter?
So the question is, how do you ensure if all of these processes are just running asynchronously, how do you make sure that each of them is actually, for example, on the same step? This is because all reduce is a synchronization point. It'll stop everyone and do the all reduce. So you have to be careful because if one of your ranks has a missing all reduce, then it will just hang. Yeah.
Why does getting the initial parameters depend on the rank?
The question is, why does getting initial parameters depend on the rank?
Are they the same? They should be the same.
They're the same. The reason is just because I guess I don't. The code for this basically puts it on the appropriate GPU.
Oh.
Okay. Any other questions? So DDP is something you implement in assignment 2, which maybe some of you have looked at or maybe not. It will be done in the context of a transformer, but this is sort of the most bare bones version, so you can see very clearly what's happening. Okay, so that's DDP. Losses are different across ranks. But the gradients are reduced to be all the same, so therefore the parameters of all the ranks are the same. right? So actually, you're doing world-size number of SGD runs, but because they're synchronized, they're doing the same thing. So you can think about this as sort of an instantiation of, analog of activation, checkpointing, where sometimes you just do extra compute because you don't want to store things. In this case, we could have, for example, shipped the optimizer state around, but that would be a bad idea because, it's much faster just to run to update the optimizer state than to actually move the optimizer parameters around. Okay, so last year I did try to do FSDP, but that was a sort of a hairball, so I'm going to skip that. And do a tensor parallel. So here the picture is we leave the data the same, and now what we're going to do is we're going to cut the model along the hidden dimension. Okay, so each rank is going to get every layer, but it's going to get only part of each layer. And what we're going to end up doing is transfer all the data and the activations around. Okay, so we're generating the same sample data, and let's look at tensor parallel. Okay, so I have the batch size and number of dimension as before, and now I'm going to before I was cutting batch size, but now I'm cutting numdim. So I have local numdim equals 1024 divided by world size, and that's 256. So each model essentially, each rank gets a part of the model which is 1 over the world size fraction of the parameters. Okay? And remember why we're doing parallelism at all is because the model won't be able to fit into a single GPU, so we're going to shard it across multiple GPUs. So the parameter matrices are now numdim by local numdim. And now each rank is going to, I'm only going to implement the forward pass here, not the whole training loop. So I'm going to start going through all the layers. So I'm going to compute the activations first. So this looks pretty normal, except for remember the activations are actually batch size by local numdim rather than numdim because each rank only has a fraction of the activations now. But now once I get the activations, I need to communicate. And here what I have to do is I'm going to allocate memory for all the activations. So at this point, every one has as an x, but that x represents a different part of the activations. Okay, so now I'm going to just allocate batch size times local numdim, but world size number. So basically each rank is going to basically have enough, I'm going to just get basically have world size number of batch size by local numdim, matrices. And then I'm going to do an all gather. Okay? So I'm going to send all the activations, and this, it's fairly simple. So x, remember, is batch size times local numdim, but x is different for every rank. So when I do the all gather, I'm going to put it in activations, which has essentially a world size number of the same shape as x. Okay, so now every rank has the same activations. Now it has activations of all the models, of the whole model. Okay, and then just to concatenate them together to get x. Okay, so now x is now again batch size by numdim. Okay, and I repeat. So as you can see, this is there's quite a bit of communication that happens, which is why, remember Tatsu said that for tensor parallel, you need pretty high interconnects, otherwise you'll be passing a lot of these activations around. Okay, and then you do it for the next layer and the next layer, and you get the idea. And just to print out some output, so tensor parallel, let's see here, forward pass produces activations of basically the full size, and everyone has the same activations at the end. Okay, so backward pass I'm going to skip because that's kind of annoying to do. All right, any questions about that? Yeah.
I was just wondering why it's hard to do the backward pass.
So why is it hard to do the backward pass? I don't think it's necessarily hard, but I guess in the constrained time and space, it's not hard. It's just requires a bit more work. Okay. So now let's go to pipeline parallelism. So in this case, we're cutting the model by layers. So all the ranks get all the data, and all the ranks, each rank gets all of one layer, but they get different layers. Okay, so sample the data and run this program of this function for all the ranks. Okay, so here I'm going to figure out how many layers go in each rank, which is 2 here. So I have a 4-layer network. I have two ranks. So each rank gets 2 of the layers, just like this picture, actually. And here I'm going to just allocate the parameters just for the layers that I need. Okay? So I'm going to do the forward pass. Remember, there's a further optimization that you do, which is, if you just do it naively, you get these pipeline bubbles that Tatsu talked about before. One way to sort of mitigate that is to break up the batch into micro batches. So here I'm going to divide this batch into batches of size 32, so 4 batches of size 32. And then now the idea is that every rank is going to essentially wait for the previous rank to pass it to the activations. It's going to apply those layers, and then it's going to forward it to the next rank. So starting at the base case, we have rank equals 0. That's just the data. So I'm just chunking the data into a bunch of micro batches. And going through each of the micro batches, first I receive the tensor. So I'm using these point-to-point primitives now instead of the collective primitives. And I essentially basically receive the tensor x. And then I'm going to compute the layers that are assigned to this rank. So in this case, there's only 2 of them. And then I'm going to send it to the next rank. And then again, send is a point-to-point operation. And then the next batch, I'm going to do the same thing. So I'm going to skip that. Okay, so that's basically it. So pipeline parallel, at least the very naive version of it, is relatively conceptually simple. But as Tatsu mentioned last time, there's many things that are missing from this basic implementation. Overlapping the communication and computation is something we're not doing at all here. For example, receive and send are synchronous, but you should really make them async. And also the order in which you do the forward. Actually, this is just the forward even, not the backward. But once you have the backward, then you have to figure out how to interleave the forward and the backward steps. Yeah.
I guess maybe what you just mentioned about the async not being shown here is I guess in actuality the GPU will be sort of listening whether another one passes something to it, and it's kind of can be kind of competitive as in a event-driven way. Sort of it only starts processing once the layer before it passes to it, and then it starts processing.
So the question is this kind of like event-driven programming where you're just kind of waiting for things to happen? And I think event-driven programming, you basically write these handlers, and then whenever stuff happens, maybe you get a mouse click, maybe you get a file-ready event, then a piece of code runs. That's quite different, I think, from this style of coding where everything has to work in lockstep. It is true that you're sort of waiting for the previous your rank to send you the information, but at least in this implementation, there's no flexibility of where it's getting from. It's not like it's waiting for arbitrary data to come from anywhere. I think there are ways to do asynchronous training, which was, I think quite popular, more than 10 years ago, where it's more event-driven, where you have a server that sends data, and whenever the gradients are ready, it just uploads, and then the gradients get accumulated. And if workers die, then that's sort of handled more robustly. But in modern training, despite scaling up quite a bit, everything seems to be kind of in a synchronous paradigm. Yeah, so it is true that when I say the workers are and the ranks are operating asynchronous, that's just because it's different processes. But you're still putting quite rigid synchronization on how everything is working in lockstep. Yeah?
How would you change this program to handle, to overlap the computation with the communication?
So the question is, how would you change this to overlap communication and computation? So, for example, when you send this, there's no reason to just wait for the data to be sent. You just basically fire off the send. Remember, the send actually happens on the GPU via some kernel launch, so that's sort of independent. And it can just go and process another microbatch, right away. So the way I think you would do this is there's another function called isend, which is asynchronous. Actually, this should be synchronous. Asynchronous, which returns a handle. And so you basically do all the send, and then at the end, you basically wait for all the sends to complete. And then for overlapping when you actually have the backward step, then you basically have to schedule that in here. Yeah.
Is the tensor name for send and receive could be the same? If you have multiple sends and multiple receives, how does it know which one is which?
So the question is, if you have multiple sends and multiple receives, how do you know which is which? So here, the tensor name doesn't matter. It's just whatever a variable is there. And what you're specifying is the source. So if I'm at a node and I'm receiving, then whatever the next message coming from that rank, I'm just going to put in this X and continue executing.
What if I want to do two sends from the same rank?
If you want to do two sends from the same rank to the same destination,
Order in which they run or something?
So I'm not quite sure about this, but I think if you have two sends, it's sort of put in a stream. So the order of the sends still is preserved. It's just that other stuff can happen at the same time. Like, you can send to, like, I think if you have a pair and you do two sends, then that order is preserved. But the order in which, you send some other rank is sending to another rank, it can happen at any time. Yeah.
What would happen if you just did like this dot send, but then no one's receiving it? And would it just get stopped there, or like?
So what happens if you send and no one's receives it? I think it would just stall. It would just wait. Because there's no, the process could just be running and you don't know whether it's just code executing. So you don't know if it's never going to get there or if it's just going to be a matter of time. Yeah. So the question is, what happens to the last rank? So at the end, the last rank has all the activation. So that has basically the results of a full forward pass. And then, if you implement the backward pass, then you would be actually now computing the gradient with respect to loss, and then you would go back down and send from rank to rank -1 and so on. Okay. I guess maybe I was afraid I was going to run out of time, but it looks like I actually have time. Maybe next year I should do the backward pass. Okay, so actually I'm going to finish quite early today, but so if you have any other questions, you should ask. So far we've gone through 3 simple examples of data tensor pipeline parallel. Of course, this is for simple MLPs. You would actually want to do this with your own, fancier model, like a transformer. I did argue that at least at the core ideas you can sort of understand through the MLP. I think but of course when you want to train transformer, not a deep MLP. So you still have to implement the full complexity. What's also missing is the communication and computation overlap, which is not really handled very carefully here. And there is generally a more complex code with bookkeeping. I encourage you to check out like Megatron LM or PyTorch's FSTP. It gets fairly hairy. And one of the things that I think makes some of the bookkeeping, at least for, let's say, FSTP, and you'll be exposed to this in A2 a bit, is that if you want something that handles arbitrary architectures, then you have to figure out the parameters and do a bunch of bookkeeping and figure out where the layers are and so on. Whereas in the MLP case, it's just I've sort of made the decision that I'm going to split the model in this particularly simple way. One other thing I'll just mention as an aside is that all of what we're doing in this course is PyTorch, but it is useful to be aware of this whole other ecosystem around JAX and TPUs, which is actually kind of nice in some way. And the idea here is JAX allows you to just define the model. It defines the sharding strategy, and then the JAX compiler handles the rest. So there's this toolkit that we developed called Levanter based on JAX. And I'll just show you a snippet of what happens. So this is FSTP in 10 lines of code. And basically you have a model, and then you just say shard with this particular, I don't expect you to kind of read this exactly, but basically you define which dimension you're going to shard by, and then that's it. And similarly for tensor parallel, you're just saying I'm going to shard the model along the, you can shard by on the head dimension for for attention, and also you can shard based on the model dimension. So in some sense, this gives you a sort of conceptual simplicity of what you're trying to do is you have this basically computation graph, but it has these kind of dimensions, the model dimensions, the embedding dimension, the attention sequence dimension, and JAX allows you to basically just specify which dimensions you want to cut by and also define a mapping from that onto the actual TPUs. And then the JAX compiler magically just figures out how to compile that down into the primitives that shuffle things around. So this is much more higher level than doing the operating with the collective communication. But we're sticking with PyTorch because it allows you to see kind of underneath the hood what's actually happening. But if you're actually doing this in the real world, obviously you don't need and you probably shouldn't implement all of this from scratch. Okay, so that's the end of the JAX digression. So just summarize, we've seen many ways to parallelize so far. And each of these ways of parallelizing is you can think about just like splitting either the model or the data along some dimension, either the data, the batch dimension, the width dimension, or the depth dimension, or the context length dimension. We also see this kind of recurring theme of recomputation. You can kind of recompute something from scratch, or you can store it in memory and suffer the data transfer cost. Or now in the multi-GPU, multi-node setting, you can actually store on another GPU's memory and then communicate, which is even slower. So there's kind of these trade-offs here, and often recomputation is actually can be better, but obviously you can't recompute the whole thing, and often you're either communication or memory limited. A final word is that it is the case that hardware is getting better. So you might think that, well, maybe none of this is really necessary because in 5 years everything will fit in L1 HBM. So this is not going to be the case because those might grow quite a bit, although there are still physical limits. We'll always be ending up with bigger models that sort of are at the limit of what the hardware can do. So this hierarchical structure, ever since computer systems was a thing, has always been with us, and it will always be there. Okay, that's all I have for you today. So I can take any questions. Yeah.
So increasing beta parallelism, even with the same set of parameters, the forward pass might be different because your normalization might be a function of the input data set. For example, in class form, you have learning means and variance. So then, does that affect training enhances, or people just don't handle it?
So the question is, in data parallel, you're saying that even though the parameters are all kind of synchronized, there could be other things that depend on the data, like in batch norm. So I don't actually know how you. Batch norm is always kind of annoying. So I don't know exactly how you would do that off the top of my head. And I guess at least in the LLM world, that doesn't really show up because layer norm is used. And as long as you initialize all the parameters and they're using the same random seed, you'll be fine. I mean, there could be like non-determinism issues on the GPU, but hopefully those are minor. Yeah.
Is there a similar way, a similar easy way for PyTorch with parallelism if I'm training which I use with PyTorch?
So the question is does PyTorch have some niceties as well, kind of like what Jax offers. Is that?
Yeah.
So, I mean, PyTorch does have the FSDP library, which you should absolutely use if you're not taking this class, which basically is a wrapper. You define any model, and it just does FSDP on it. I think that now, if you're asking how well it can allow you to more do custom sharding, I think there are some things that are coming, but it's not as, I think, as developed. I mean, I think there's sort of this, I think, spectrum between the JAX world where you sort of declaratively define things, and I think the Google infrastructure, if you stay within the JAX TPU system, is pretty well developed. But then if you look at kind of DeepSeek, which is a kind of the opposite end, where you have these GPUs with actually really bad connect, which means that they have to go in and hack, they actually go to the kind of nickel level and actually do a bunch of things which I don't quite understand to eke out the performance. Whereas if you're writing a JAX, you just kind of from on high declare your model, and then stuff happens. So it's kind of the ways that you leverage hardware, I think, really depends on what ecosystem you're operating in. Yeah.
Is there a way to manage the amount of recombination of activations? So you can recombine some subset of the activations for the performance. Is there an API which you can manage?
Yeah, so the question is activation checkpointing. There is an API that basically allows you to, I guess in PyTorch and JAX, to specify which parts you want to recompute, because clearly you don't want to recompute everything or nothing. Probably every few layers, probably right after like big mapmals where, for example, if you have, let's say, mapmal and then pointwise linearity, I don't think you need to store like 2 copies of. Basically, if you have 2 things where it's sort of trivial to get to, then you might as well just store one version. Yeah, over there.
Do you think GPUs are being replaced by like specific hardware or like more specialized hardware?
So the question is, are GPUs going to ever be replaced by transformer-specific hardware? So you're seeing this in the inference space quite a bit already with like Grok and Cerebras have specialized hardware that can do inference. And also, I guess, training. Cerebras does training. So basically those hardwares essentially give you just a lot more kind of on-chip memory. I mean, that's basically the name of the game. I think Cerebras has like a huge, essentially effectively a L1 cache, so you don't have to move things off. And I think a lot of simplifications can happen because GPUs there's a lot of baggage actually if you think about, because they were designed in an era where you had to do a lot of branching and various types of ad hoc computations, which are not really needed in the deep learning regime. So I think there are quite a few opportunities to improve the hardware as well. I think there was a hand back there, and
I don't know if this is like the right question that I'm thinking about, but in the context of the lecture, it's basically a model that's being trained in one go that's being optimized in Tensor, but I'm wondering if any of the techniques that we're talking about can be used to incrementally train a model, for example, as you get new training data. Not just to like fine-tune, but actually to kind of recalculate everything without having to recalculate everything.
Yeah, so the question is, can these techniques be used to essentially do continued training? Yeah, absolutely. So if you think about the unit of what we're working on, it's just doing gradient steps, right? So if you take a half-train checkpoint, you can just continue doing what this is. There's nothing specific about starting from scratch here. I think there was a question there.
So on the model-specific hardware end, the previous question, presumably there's a physical technical reason you can't make nodes much larger than they are currently. What's the change that you're talking about? So if you could just make GPU nodes infinitely, as big as you wanted, people would do that. So presumably there's a hardware reason that's not possible. So what's the actual advancement being done for the rock-specific hardware you mentioned?
Yeah, so the question is, there are physical limits for sure for a GPU. Let me just go. So so you can't make GPUs obviously infinitely large or infinitely dense. I mean, there's also power issues. You need to get rid of all the heat, and there's only so much kind of bandwidth that can fit. So I don't know the exact details, but at least in some of the Cerebras case, I mean they sort of have this way of manufacturing basically the chips so that the memory is kind of on the chip. So I guess it's just a way of putting it on there, and I think that there are obviously trade-offs because it comes at a cost of not having as much flexibility. But in general, I think the way to maybe think about this more broadly is that GPUs were still developed in kind of the CPU era where it's much more control focused. I have code that I'm executing, that's the sort of first class citizen, and then data needs to be moved to execute to handle the code. But the big difference with deep learning workloads is that it's all sort of data flow. Like the computation graph, if you look at these, is like static. You know from the beginning exactly all the computations that are going to be done until essentially the end of training, right? So using that knowledge, you should be able to kind of lay out your computation in a much smarter way than having to deal with the flexibility and uncertainty over ad hoc computation. Okay, maybe a few more questions and I'll end there. Yeah.
Is the computational graph usually stored in the CPU or in the GPU?
So the question is, where is the computation graph stored? Well, the code is all this code is running on this CPU, but when you call something like the PyTorch function, it needs to run on GPU, then it launches kernels under the hood, and the kernels are code that runs on the GPU. I'm not sure if that. So I guess maybe another answer is that the computation graph is more of a conceptual. It's not like there's a graph literally that's being, I guess there sort of is, but it's not like the graph gets put on the GPU. If that makes sense. Okay.
So these communication primitives that we have, like receive and send, so they are actually CPU instructions or are these programs indirectly on the GPU?
So the question is, the communication primitives, are they CPU or GPU? So these collective operations are, in some sense, abstract specification of what types of operations need to happen, which can happen if you remember this PyTorch distributed has different backends. So it could happen on GPU or happen on CPU.
But when they're happening on CPU, is it is the CPU sort of scheduling them, or is it like kernels which are independently?
Yeah. So the CPU sort of drives, basically, is the sort of the master still, and then when you do a collective operation, it calls the nickel library, which launches, which is it's still CPU, and then it launches some kernels that move data around. Yeah. Okay, maybe this is a good place to end. All right, I will see you next Monday, or Tuesday, rather.